Okay, we'll begin. I hope you guys enjoyed your slightly longer weekend, and we'll do an attendance poll. Okay, so go ahead and log into the online polling tool, and so for attendance today, we'll say I don't know, select option D for attendance. Today's attendance. Okay, we'll so log into the online polling tool. I received some feedback that when I asked real questions in class, it was too stressful. So that's fine. We'll just do attendance. Okay, that's fine. All right, we've got a decent amount to cover. Most of our stuff today will be handwritten notes. Just a heads up, and so we'll do that. Okay, and today's topic is root finding methods. Okay, the idea behind root finding methods is that we have some function f. Okay, we have some function f of x, and what we want is we want to find the values of x, the value of x, so that f of x is equal to 0. Okay, and these are known as the roots of x, the roots of f. Okay. And you know, algebraically, this is easy to do. We just take some function, we set it equal to 0, we do algebra, and we solve for x. All right, that's simple enough. Okay. Sometimes we have a complicated function, a function where it's not so easy to do algebraically, and so what we have for our tools are just some numeric methods for finding these roots if we didn't want to bother solving kind of the algebra, right? So with algebra, we set f of x equal to 0 and solve for x. Okay, and what we are doing is with numeric methods, you know, we don't do algebra, and we just follow some rules, follow an algorithm to help us find x. Okay. Just follow an algorithm to help us find x. The limitations, though, are because we're doing this on a computer system with floating point numbers, it is possible, you know, not to get the exact value. All you can do is get like a value that's very close to the true value, right? So, you know, there are limitations. In that, you know, our answers will generally be approximations. Generally be approximations because of floating point yeah, because of floating point, really. Okay, and so I will cover today, I'll cover 1, 2, 3, 4. 4 different root finding methods, and these are all just different methods to find where the function crosses the y-axis, to find where f of x is equal to 0. All right, okay. And if you got here just a little bit late, you have to select option D in the online poll for attendance. I'm going to go ahead and close down the poll in a couple minutes here. And if you come later than that, then you don't get credit. So, okay. All right, so our first method is called fixed point iteration. Okay, and a fixed point is a fixed point of some function g of x is where g of x is equal to x. So for example, if g of x is equal to x squared, then x equal to 1 is a fixed point, because g of 1 is 1 squared, which is equal to 1. So g of x is equal to x. That's a fixed point. Okay, so to use fixed point iteration, what we do, to use fixed point iteration to solve for roots of f of x, what we do is we rewrite f of x equal to 0 into the form g of x equal to x. Okay, and then thus finding a fixed point of g is equivalent to finding a root of f. Okay, so here's just kind of an examples, and this is from the textbook Spurs. Chapter 10, okay? And so let's say f of x is equal to log of x minus e to the negative x. And we want to find where this function is equal to 0, so we want to find roots of this function. Okay, so we have several options, okay? Options to get it into the form of g of x equal to x, right? Okay, so I'll say option 1 is I will take, I'll just write log of x minus e to the negative x equal to 0. We will rewrite this. We will just move some terms around, and I'll add e to the negative x to both sides. And then I will raise both sides to e. And so here I will get x is equal to e raised to the e to the negative x. All right, and so we will say, and we will set this thing equal to g of x. Okay. Here, let me actually write this. So we'll say let g of x be exp e of exp of negative x, okay? And then solve for g of x equal to x. Done. Then you will have roots of f of x. So that's one option, okay? The other options are even easier. Option 2, you've got log of x minus e to the negative x is equal to 0. And then all we'll do is we'll just do x minus this side and x minus that side. So I'll have x minus log of x minus e to the negative x is equal to x minus 0. Right? And so that just becomes x. And so we'll let g of x equal to x minus log of x plus e to the negative x, and then solve for where g of x is equal to x. Right? And then option 3 is you, instead of saying x minus the left side and x minus the right side, we'll just do x plus the left side. X plus log of x minus e to the negative x is equal to x. And we'll let g of x equal to x plus log x minus e to the negative x. And we'll set, and in all of these things, we just solve for where g of x is equal to x. So, given any function, there's like an infinite number of ways to rewrite the function to be to have it in the form g of x is equal to x. Is this okay? So we rewrite f of x into g of x, okay? And then once we have that, then fixed point iteration the algorithm says start at some arbitrary x and we will call this x at time 0, and then find g of x0, okay? And this will give you some new value, okay? Find g of x0, and then use this g of x0 as your next x, okay? Next x of 1, okay? And the algorithm is just this. X at the next iteration, x at n plus 1, is equal to g at x time n. So this is just the next guess, x at time n plus 1, is g at the g of the current guess. X of n, okay? And this works if the derivative, if the slope at g of x is, if the absolute value of the slope is less than 1, okay? Otherwise, it will diverge. So let me just kind of illustrate how this might look. this. So this line represents the line y equal to x, okay? And let's say we've got some function that goes like this, okay? So, sorry. Oh, here, let me close our poll. Okay, so we'll start at some value x sub 0, okay? And at x sub 0, this is the value of g of x sub 0, okay? What is g of x sub 0? Well, if I look at g of x sub 0, and I just kind of come across horizontally right here, because this location right here, this is going to be, this height is g of x0, and that means this location here, if I, this is g of, this location here is the equivalent value, right? G of x0 is right there, because this line represents where x and y are equal, okay? And so I will use this as my next guess, x sub 1, okay? And then so basically if I calculate what is x sub 1 at this location, I'll use a different color here, then this location right here, this is g at x sub 1, okay, which turns out to be like right here. This is g of x sub 1, and basically I come across to here, and then this location is g of x sub 1. This is going to become my x sub 2. And you can see that I would just kind of iterate and get closer and closer and closer until I reach this point, this being the desired fixed point. This is where g of x is equal to x. If the slope is greater than 1, if the whether it's if the absolute value of the slope is greater than 1, then you'll get a diverging setup. Okay. Okay. Let me kind of I'll just write this in pseudocode. Okay. So you can have fixed point. This is going to be some function of g x0 and a tolerance value, and I'll just say the tolerance will be 1 times e to the negative 6 or something like that. Okay. And basically I will start off by saying x old is our current value, x0, and then x new will be g of x old. And then I'm going to start a loop. I will say while, and I'll say the absolute value of x old minus x new, while that is greater than our tolerance, then repeat the following. All you have to do is just take the current new value and call that the old value, and then find g of the old value and call that your new value. Close that the loop, and then at the end you will return your latest value. Okay, and obviously g has to be some kind of function, right? All right, is that okay? Fixed point iteration. All of this is covered in your textbook as well, so look at the relevant pages there. Okay, we have another root finding method, and this is the Newton-Rapson method. You guys might have covered this in your calculus class. Another root finding method, and this is Newton-Rapson. Okay, and the way this works is, let's say you got, let's make this a little bit curvier. Okay, so this is our desired root, right? This location right here, this is our root. And what we do is you start at some x0, okay, and then you go to this location. This is going to be f at x0, so you find f at x0, and then you draw a tangent line that goes down to the y-axis, okay? So draw a tangent line from x and f of x, x0, f of x0, to the x-axis. Okay, and that location will be x1, and then repeat. So we start off at x0, we go up to f of x0. I draw a tangent line from this location. Okay, so what does a tangent line right here look like? Something like this, okay? So I draw a line tangent to this point, and where it crosses right here, this spot is going to be x sub 1. Then I repeat the process. I find, okay, what is my value at this point? This is going to be f of x sub 1. I draw a tangent line at that location. So maybe it looks like this. I don't know. Okay. And then this location here, this will be x sub 2, x at time 2. And so on, and we repeat the process, okay? We find the value, we draw a tangent line, and eventually this will close in on where the root is. So this is x at time 3, etc., etc., etc. All right, does that kind of make sense? Okay, so what is the location at x at time 1? Okay, well, all right, what's the definition of slope? Like when you learned algebra in 8th grade or 6th grade or whatever it was. Slope is rise over run, thank you, okay? And, okay, and so what is x1? x1 is equal to x0 minus the run, right? So x1 is equal to x sub 0 minus the run. Or let me just generalize this. And so I will say x at time n plus 1 x at time n plus 1 is going to be x sub n minus the length of the run. Okay, is that good? Okay, and this here is the rise. So how do I calculate the run? Well, I just do a little bit of algebra here, and I will get run is equal to the rise divided by the slope. Yeah. The run is equal to the rise divided by the slope. Okay, what is the rise? The rise is equal to f at x sub n. And what is the slope? The slope is going to be f prime at x sub n. Okay, so this, the general algorithm is just this. X at time n plus 1 is equal to x sub n minus the run, which is the rise divided by the slope. F at x sub n divided by f prime at time x sub n. So given your value x sub n, if you'll need f, and you'll need f prime of x sub n, and then that will give you your next value. Is that okay? All right, so let's say we wanted to do f of x is equal to x squared minus 4, okay? So it's easy. We know that the root at x equal to 2. But anyway, so what we will do is I will say f is a function of x, and what it will return two things, okay? First, it's going to find f of x, and this is going to be x squared minus 4, and then we will have f prime, and this will be 2 times x. And what it will return is our function will return a vector consisting of f of x and f prime. Okay, thus if I call f on 5, what it will return is it will return 21 and 10. It will return a vector of 2 values, and then I can call, f5 sub 1 is going to be 21, and f of 5 bracket 2 is going to be the value 10, right? Okay. Earlier we said x of n plus 1 is equal to x of n minus f of x of n divided by f prime of x of n. Okay, and then so we can write our Newton-Rapson. This is pseudocode. Will be a function of f, x0, and our tolerance, which I'll default to 1 times e to the negative 6. Okay, so we will set our x sub 0 into x old, and then we'll run a while loop. And we'll say while the difference between x new and x old is greater than some tolerance, then continue this thing, okay? So x old we'll take our current new value, okay? And then all we have to do is the new value is going to be x old minus f of x old. Take the first value divided by f of x old, the second value, okay? And that closes off our while loop, and then at the end, return x new. Okay, this is just pseudocode, so does that make sense? What's that?
What's the x new here?
What's the x new? It's just whatever is gonna get propped up in here, okay? So I guess you have to define it somewhere in here, but it's just the next iteration, okay? Basically, I'm calling x of n is x old, and xn plus 1 is gonna be x new, okay? At each iteration, the next value, your new value of x is just your old, and you apply the root finding algorithm to get your next one. All right. Does that kind of make sense? All right. Let's try another one then, okay? We're just gonna keep hammering these out. I know I'm going through these quickly, but they're also all covered in your textbook, so I recommend you check out the textbook as well. Okay, secant method is similar to Newton-Rapson, except you don't calculate derivatives, and instead you have two starting points, okay? So let me just kind of illustrate what secant method looks like. Is you've got some kind of function. Let me just, I'm having trouble drawing a curved line. Okay. And basically, you'll have two starting points. So we'll have x0 and x1. Okay. And instead of finding a tangent line, you say, okay, here I've got x0 and here I've got x1. And this up here is f of x0, and this is f of x1. And instead of doing a tangent line, you draw a secant line. So it's kind of like Newton-Rapson, except you're drawing a secant line through those two locations. X0 is right there. Okay. And then at your next iteration, so this right here is going to become x2, and then you go up, and you say, okay, well, now we're going to do a secant line right here from using x1 and x2. All right, and then so now we get x3, and then you get furthermore another secant line. So you come up to here, and oops. so on and so forth, okay? So you just continue the path until you get to the root. Okay, how do we figure out your next value here? Okay, how do we know what x2 is going to be? Well, x2 is going to be equal to x1 minus the run of this triangle, right? So I've got the run, I've got the rise, okay? And so here, this x2 is going to be x1 minus, and earlier we said slope is equal to rise divided by run. So run is equal to rise divided by slope, right? So here I'm going to write x1 is rise divided by slope. So x2 is going to be x1. My rise here is f of x1, and then I have this slope term, okay? Where is the slope coming from? The slope is coming from this triangle right here, yeah? Okay, so the slope is determined by the blue triangle. Slope comes from blue triangle. Okay, what is the slope of the blue triangle? Okay, this is the rise divided by the run there, right? So the rise over run, the rise is going to be f of x0 minus f of x1. Is that okay? That's the rise, that's the difference there. And then the run is going to be x0 minus x1. All right. The textbook flips these around and writes it this way: f of x1 minus f of x0 minus divided by x1 minus x0. But you can see that these are equivalent, right? Okay, so this is how the textbook writes it. And so basically, we're just going to plug this in. This is going to be the slope of blue triangle. We're going to just plug that into here. So our x2 is going to be x1 minus, and I'm going to just do f of x1, and I'm going to just flip this. So it'll be times x1 minus x0 divided by f of x1 minus f of x0. Is that okay? And then, here, let me just slide that up. Okay, and then so to generalize, we've got x sub, at the next location, x sub n plus 1 is going to be x sub n minus f of x sub n times x sub n minus x sub n minus 1 divided by f of x sub n minus f of x sub n minus 1. And this would be our secant method. Is that okay? And I'm not going to write up the pseudocode here, but but I think you guys can figure it out. You just need 2 starting points. Okay, so the advantage of the secant method is that you don't have to calculate derivatives, right? So the Newton-Rapson method, you needed to calculate your derivatives. You need to calculate f prime to figure out your slope. Here we are getting kind of a stand-in for the slope by using the secant lines. Okay, and the very last method. This one is called the bisection method. And what's unique about this one is that this one is guaranteed to work. Okay, the other methods are not guaranteed to work. Like you need to have derivative, like your functions need to be differentiable and all sorts of stuff. This is guaranteed to work as long as f of x is continuous. Because of the what's the thing called? Intermediate value theorem or whatever? I don't know. There's like a rule in calculus, right? So basically the idea is you've got some function and you start off with some endpoints, okay? You've got 2 endpoints. And I will call this x L1 and x R1, okay? So x, the left endpoint at time 1, and the right endpoint at time 1, okay? So you've got 2 endpoints. And I didn't do a very good picture here, okay? But all right, so let's say you're gonna find xm, which is going to be the midpoint xl1 plus xr1 divided by 2. That's your midpoint. Okay. And, oh, I'm sorry, I need to back up. So the 2 endpoints xl1 and xr1, the one thing is that if x of L1 and f of R1, x at R1, have different signs, so if one is positive and one is negative, they need to have different signs, you know a root exists between them. Okay, so that's the condition, right? So you got 2 endpoints, L1 left point and your right point, and then they have different signs, okay? Then you find the midpoint, xm, okay? And you find the sign of xm, f of x at the midpoint. And basically, you keep the pair of points that have opposite signs. That have opposite signs. So once we find this, then next iteration, xl2 is equal to xl1, and then xr2 is going to be xm. Okay, so we find this one's positive and this one is negative. So we keep these two, and these are now our new endpoints. And then we find, so this becomes x at L2, this becomes x at R2. And then we find the midpoint here. So we're going to get xm here. And we go, oh, okay. Well, the sign here is right here. Okay. So at the next iteration, then XL3 will become the current midpoint, and R3 is going to be your current right midpoint. Yeah. And then you just continue, and you just keep finding the midpoint and keeping the pair of points, endpoints, so that the function at those endpoints have opposite signs. And this is guaranteed to kind of converge around the root. Does that make sense? Okay. The only drawback with this is that it's slow. Okay. You're just constantly having things, and so it's a little bit slow there. Okay. But that's the bisection method. Okay. We'll end here for now, and we'll see you guys on Friday.